All right, so in order to describe the population distribution of particles over the course of very different energy levels, what we need to do first is we need to develop some sort of way to describe the entropy of the system. All right, and so what we're going to do is we're first going to consider a system that's made up of n identical particles, and these particles can exist in different energy levels, specifically t number of different energy levels. So the way I want you to think about this is imagine we have what's known as an energy ladder, where energy is represented by epsilon sub I, and in this energy ladder we have different energy levels. So the ground state, energy level 1, energy level 2, energy level 3, and so on and so forth until we get to the highest energy level T. And so for a given temperature, there exists a different number of particles in each of these different energy levels, right? So let's say that for some given temperature, we have one particle that's in the lowest energy level, then we have 3 in energy level 2, 1 in energy level 1, and then maybe 2 in that highest energy level. Okay? And for the type of system we're considering, let's say that temperature, volume, and the number of particles are fixed. Okay? All right, so we have these sorts of different energy levels, right? And so what we want to do now is we want to estimate the number of microstates that are possible for arranging these different particles, right? And so essentially what we're doing is we have n number of particles, and we're arranging them in different sort of levels, right? And so in order to calculate the overall number of microstates, the omega total, essentially all we're doing is calculating a multinomial coefficient, right? Because we have n number of particles, and then in energy level 1 we have some n1 number amount in there. In energy level 2 we have some n2 number. Energy level 3 we have some n3 number, dot dot dot, till we get to that top energy level. And so for this omega, remember we have these factorials here, okay? And so this just based on intuition, this is how we would calculate the number of microstates. All right, but we want to, because we're dealing with factorials here, we want to be able to simplify this somehow, okay? And so for this omega t, the way we have it, let me just copy this and paste it here. The way we have it here, in order to kind of simplify it, what we could do is we could apply Stirling's approximation, so we don't have to deal directly with these factorials. So if we apply Stirling's approximation, we could rewrite all of the factorials like this. So it's going to be n factorial is n divided by exponential to the 1 raised to the e. Okay? And then in the bottom here, we're going to have n1 divided by e raised to the n1, n2 divided by e raised to the n2, n3 divided by e raised to the n3, and then dot 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 till we have nt divided by e raised to the nt. Right? So all we did here was just apply Stirling's approximation. Right? Now, what we have to recognize is here we essentially have e to the negative n, and then in the denominator we're going to have e raised to the negative n1, and then we end up just multiplying it such that in the denominator we're also basically going to end up with 1 over e to the n. And so what that means is we could cancel out all the exponentials. So I'll just cross out the e's here. And what we're going to be left with is n to the n divided by n1 raised to the n1, n2 raised to the n2, n3 raised to the n3, dot dot dot, nt raised to the nt. Okay? Alright, what I'm going to do now is I'm going to kind of divide out, bring this to the denominator, right? And because this is raised to the n, I can manipulate my log rules such that I could split this up into n1 plus n2 plus n3 dot dot dot. And so by doing that, essentially I could rewrite omega like this. n1 divided by n raised to the n1, n2 divided by n raised to n2, n3 divided by n raised to n3, dot dot dot, nt divided by n raised to the nt. And 1 is just on the top. Alright, and so what I have here is n1 over n. And just based on the definition of probability, we know that n1 over n would just give us the probability of a molecule ending up in the first energy level. And this one will be P2, this one will be P3, this one will be PT. And so our omega total is just going to be equal to P1, N1, P2, N2, P3, N3, dot dot dot, PT, NT. And that's raised to the 1. Alright, so that's what our total number of microstates is for this sort of energy ladder here. Now, if we want to calculate the entropy, we know that by definition, entropy is just Kb natural log of omega t, or omega total. Okay? And so if we plug in our omega total into this equation here, essentially what we get, and I'm going to write it in compact form, is this. N sub I natural log P sub I, and this goes from I to T. Okay? Alright, and then what I'm going to do now is I'm going to divide both sides by the total number of molecules. And so S over N just gives us S squiggly. And by dividing both sides by N of Ni over N, that will give us probability again. So what we get is S squiggly is equal to negative Kb. The summation of I is equal to 1T Pi ln of Pi. Alright? And so, starting with this sort of kind of generalized system, to describe the entropy of that system, we actually have a very simple sort of equation, right? And this equation we have, it's a fairly general equation, right, because we started with a general system. And so essentially, this is an equation that relates the probability distribution of a system to its overall entropy. So we have some sort of entropy probability relationship. This sort of relationship was discovered by a scientist with the last name Shannon. So typically it's called the Shannon entropy equation. And this equation not only deals with particles in different energy levels, but because we started with such a generic sort of system, this equation can be extended to describe systems in which you're dealing with bits, like in designing a computer chip or storing information, right? And so this Shannon entropy equation is used to analyze a lot of different types of systems.